a mouthful. Okay, see if I can figure this out. Is there life on Mars? Something I've wondered about ever since Viking days, back in 1976. Back in Viking days, we saw these images that showed ancient stream beds, apparently, flowing across, or once flowing across the surface of Mars. When I'm a 16-year-old kid looking at that, I think that's not so different than the Earth. More recently, with the Mars Reconnaissance Orbiter, we've gotten these images, and we're going to come back and talk about this image in a little bit when we talk about the 2020 lander. But collectively, these kinds of images really drive home the importance of water in that life question. On Earth, when we think about life, one of the key things that we have to have are water that's present and chemically water that is habitable. And we start to wonder when we see these sorts of features on Mars if, in fact, that could have been the situation on that planet. So we've been to Mars. I mean, this is one of these slides that I put up here and say, why are we going to Mars again? Haven't we been there before? I mean, look at this. There's 1, 2, 3, 4, 5, 6, 7 landing sites. Well, Mars is a lot smaller than the Earth, that's true, but there's no oceans. And so the land surface area of the planet is about the same as the land surface area of Earth above sea level. And if you'd been to 7 places on the Earth, how well would you say that you knew the Earth? Especially when you consider that the places that we've been able to land, by and large, are often relatively benign in the sense that they don't offer a lot of hazards. And so accessing the very rocks that we might be most interested in becomes a little problematic if you haven't been there more than a few times. So wanting to go back, wanting to build on the successes of our prior exploration, and trying to understand this question of habitability on life on Mars sort of drives the research that's been occurring in the Mars program for the last 20 years. So first what I'm going to do is I'm going to talk about our little twins here, Spirit and Opportunity. I'm kind of in mourning about Opportunity. The mission was officially terminated a couple of months ago. In reality, it ended last summer. There was a global dust storm that enshrouded the planet for a long period of time. We were unable to get enough sunlight on the solar panels. The rover stopped functioning. We had hoped that when the atmosphere cleared that it would come back to life, and it did not. Spirit stopped working in 2010, but both of these missions were supposed to last about 90 days. 90 sols on Mars is just over 90 days on the Earth. And so when you start talking about 6 years for Spirit, almost 15 years for Opportunity, you can start to see that we really did have quite a bonus in terms of the functions of these rovers here that you see on your left. The Curiosity rover is really a different beast. The Spirit and Opportunity are sort of the size of a golf cart, whereas Curiosity is about the size of a Mini Cooper. Spirit and Opportunity have wheels to get us where we want to go. It has an arm that we can stick out. It has instruments that we can look around and find things interesting and interrogate with our arm. But with Curiosity, we have all those things and an internal lab where we can actually heat up the samples, zap them with X-rays, and say something very specific about their chemistry. Really get at that question of habitability. So for Spirit and Opportunity, kind of field geologists on Mars. For Curiosity, making that next step, kind of introducing the biochemistry aspects of this to really poke at that habitability question. I'll talk a little bit about some of the results from Spirit and Opportunity, move on to Curiosity, a hint, if you will, about some of the things going on with the most recent lander, InSight, that I'm also involved with, and then I'll wrap up with the 2020 rover and how we picked the landing site for where it's going to go for this next step in the process. One of the things that I would point out as we go through this is a number of orbital images that I'll be showing that are from the HiRISE camera on board the Mars Reconnaissance Orbiter, or in the previous slide, from the XRISM instrument on board that same spacecraft. I'm also involved in that mission, and those things allow us to not only provide sort of an overview of what we see on the planet, but then in turn, once we've landed somewhere where we think is interesting, provides the context for interpreting what we see in one spot. It allows us to sort of extrapolate those results over a broader area. Okay, so as I said, Mars exploration rovers, or MER, Spirit and Opportunity, field geologists on Mars. We've got our 6 wheels, we got our mast up there that looks around. It allows us to pick out interesting targets, drive up, and then out on our arm, which is about the same length as my arm, We've got several instruments that allow us to interrogate the rocks in front of us and even grind off some of the crud to get at a more pristine surface in between, underneath. And so what we did as we drove around is we tried to understand the role of water in shaping the surface. And we went to two very different places. And I'll start by talking about Spirit. Now, the Spirit rover went to a place where we thought this large crater that you see here, if I'm probably going to screw this up, there we go. This large crater that you see here, Gusev crater, has a channel that flows into it. And then you can notice that the wall of this crater is much higher on this side than it is over here. And the sense from the orbital data was that this channel had breached the rim of the crater, had carried water and sediment into the crater, partially filling it, and that what we see there are ancient lake beds. And so if we're wanting to understand the role of water in shaping the surface, then based on what it appears, or the morphology, this is a good place to go. Now, we also realized that if there was a lake there, it was a long, long time ago. And so one of the things that was a concern is we also saw signatures of volcanic materials. And the concern from day one was, are we going to be able to see the putative lake beds, or are we going to be thwarted from that by looking at all the volcanic material? Well, when we landed, we did in fact land on the surface of a basaltic plain, an ancient lava field. And we did not see the lake beds that we hoped to see there, but we did start to see off in the distance what we call the Columbia Hills, named for the Columbia astronauts, that poke up. They're older rocks that poke up from beneath these lava plains. And so after spending a little time out here on the lava plains, we headed off over towards the Columbia Hills. Now you'll notice on most of my slides in a box, you'll see something about whether these are false color or approximate true color, and it'll say something about how they were processed. And I'm not going to dwell on that anymore, other than to say sometimes we use false color because the different bands that we look at in the terms of the light, much like with vegetation in the near infrared, looks very bright red, and you can say something about the health of those trees or those bushes you're looking at. By looking at rocks with different wavelengths of light, you can start to say something broadly about their likely chemistry. So sometimes we use false images, color images that emphasize those things, and sometimes we use approximate true color. So you'll see that on here. You'll also see the color of the credits related to each of these. So off we went to the Columbia Hills to try to get a sense of these rocks that poked up from beneath. Here's our traverse. We landed up near a small crater called Bonneville Crater, the heat shield, the piece of the spacecraft that was coming through the atmosphere that was blasted off before the parachute came out, landed on the rim, and we went across this sort of basaltic plain, getting up into the Columbia Hills that you see over here. And what I'm going to focus on is not so much any of this, but what we ended up at down here in an area called Home Plate. Now, the names that we have for these things are often a little bit whimsical in terms of what's going on at the time. So you've heard about blueberries, and I'll talk about those a little bit. We're eating a lot of Ben & Jerry's ice cream at the time. And the false color images of these little spheres that, again, we'll talk about, were purple, so they look a little bit like blueberries. For Home Plate, we got there at about the time spring training was happening one year. So again, it's a baseball name, and we actually had a number of baseball players that were involved in terms of some of the rocks that we were looking at. So off we went to Home Plate. Here's a zoom in. This is one of those orbiter images. This is from HiRISE. And what's very interesting about this is you can actually see the Spirit rover sitting right there. Remember, that's the size of a golf cart. So we're looking down from space at this. Here is Home Plate. Okay, it's about 90 meters across, or a little less than 300 feet. Here's our rover sitting here. And there's 1, 2, 3, 4, 5, 6 of these things that were very obvious from space in terms of their presence, but largely unknown in terms of their origin. And so we really wanted to try to understand these, and the next few images that I'll show you are from right around Home Plate. Now here is, from about the location the rover was in that previous slide, looking at the edge of these rocks. They're not really curved layers. It's because the rover drives up and its camera does this and then it does this. So these are flat-lying layers, and the next slide I'm going to show you is going to zoom in on this area right here. Notice these layers, they get finer grained as you go up. Here is that area. Up is to the upper left. And you'll notice that this rock, actually, here's a flat layer. Here's a whoops, it digs down around, and then here's another flat layer. This is something on the Earth that's very well understood. It's called a bomb sag. And when you have a volcano that's erupting and throwing out pieces of pumice and rock, if the ground around it is wet, when they hit, they kind of go splat. and they deform the layers, and then more ash and stuff comes out and they bury it. So when we see this sort of thing, we start to think right away that in fact when this volcano was erupting to form these things, it was wet. Okay, that's very different than it is on Mars now. If we look at some of the other areas around this home plate, we see this sort of thing, this bright white soil. Now this is a very fortuitous discovery. It turns out that by the time Spirit got here, it had a bum wheel. It wouldn't turn anymore. So instead of 6 wheels, we had 5, and we drove backwards most of the time, and we would drag our wheel. And as it did, it actually churned up the surface. You can see the other wheel tracks through here. They're not really digging down. You just see that reddish-orange dust. But here, when we're dragging the wheel, it got beneath that dust, and it showed us this brilliant white material. And in some places, this white material actually kind of looks like these nodules that you see here. It turns out that when we measured those with our instruments on the arm, they're made up of something called silica. Okay? Silica on the Earth is something that forms the mineral quartz. But in places like Yellowstone National Park, where they have hot springs, silica is something that forms when water saturated in the mineral comes out, cools off, and precipitates this. If you've ever been to Yellowstone Park, you know exactly what I'm talking about. You'll also see these sorts of things in Hawaii and other volcanic areas. And so when we put together a story based on the things like the bomb sag that I showed you in the previous slide, based on the silica that you see here, 90% pure in some places, we start to understand that home plate, this eroded scene that we see that I showed you in the previous orbiter view, is actually an ancient volcanic field that was wet, that had fumaroles and steam vents. Might have been very much like Yellowstone, might have been very much like what we see in some parts of Hawaii. Now, when you think about habitability, you know, personally I think about places like all-inclusive clubs in the Bahamas. No. You know, you might think about the rainforest or something like that. But volcanic areas like Yellowstone and volcanic areas like Hawaii are habitable. In fact, things called extremophiles that live in hot water, that can live in chemically harsh conditions, do inhabit those places. So we're looking at a surface here that probably was habitable. Now, it didn't form yesterday. Remember, that was a very eroded picture that I showed you before, our surface that I showed you before in that picture. This is a surface that is probably 3.5, maybe even over 4 billion years old. If you think about our solar system being 4.5 billion years old, you can see that we're really pushing back the limits here in terms of how soon after the solar system formed when this was active. By way of comparison, there's very few rocks on the Earth that we see preserved from that long ago. Because of plate tectonics, because of other things, they've simply been destroyed or they're buried. So we're really looking back in time here, not only at Mars, but what was happening in our solar system. Okay, so Spirit, habitable, but kind of like volcanic in an extreme sort of way. Let's move on and talk a little bit about opportunity. Here's another orbiter view on the left. This is also an orbiter view on the right. This was taken from the Themis instrument on board the Odyssey spacecraft. And the colors that you see here are sort of painting on the occurrence of the mineral hematite. The brighter the color, the warmer the color, the reds, there's more hematite. The colder the color, the blues and the greens, the less there is. And it turns out there's not a lot of places on Mars where you see these sort of beacons of hematite. Now, some of you may have hematite jewelry that you're wearing even tonight. And one of the things that hematite is very sort of a signature for is forming in the presence of water. So unlike Gusev crater, where Spirit landed, where we saw evidence of an ancient lake bed, here we don't see any of that, but we see a chemical signature. So with 2 rovers, we decided to sort of put not all our eggs in one basket, one in this basket over here, and one in this basket over there. And we decided to go to this area where the hematite signature was in Meridiani Planum. Now, this is another one of these high-rise images from the Mars Reconnaissance Orbiter. And the resolution of that is about 1 foot. So we're really zooming in. Remember, you could see in a previous image the actual rover sitting on the surface. And what I would point out is this is a flat surface. It makes the floor that your feet are on look like the Himalayas. So this is a parking lot, folks. And when we landed there, the sense was, how are we going to see any rocks? They're not going to be exposed. Well, we got pretty darn lucky. We actually rolled to a stop in a little tiny crater called Eagle Crater. And there, lo and behold, in the wall of the crater, you can see even at this scale the layers within those rocks. So here's the broader view, and this red box here is blown up. Sedimentary rocks right there in front of us. Why are sedimentary rocks important? Because when they are deposited, they record the conditions during their deposition. Whether it be by the wind, whether it be by water, they tell us what was happening. And so whereas Spirit, we landed on a volcanic plain, we had to go to the Columbia Hills, we had a bum wheel, Opportunity rolls to a stop and voila, right there in front of it. There's the layered rocks we've been looking for. So we drove up to those. You can really see the layers here. This is from our microscopic imager. This is from the Earth in Utah. And you can see our layers here, and you can see these little blueberries that I mentioned before. Now this is a black and white image. It hasn't been colorized. But you can see already that these little sort of BBs, if you will, that's about the size they are scattered throughout the rock. And they actually sort of cut across the layers. And the best analog we can think of are these things here. They're often called Moqui marbles. They occur coming out of the Navajo sandstone in Utah. When we look closely with our instruments, it turns out these little spheres are the signature of the hematite that we saw from space. That's the hematite. And because of the way they occur, because of their spacing, because of their chemical signature, we know that these things are concretions, as they're called. They form when groundwater is saturated with a mineral to the point where it starts to precipitate it out. Now, I lived in Buffalo for a while, and they had these huge things called septaria. They look like giant turtle shells. Some of them are 5-6 feet across. They formed in black shales in western New York 350 million years ago. These things formed on Mars probably 3.5 billion years ago. And it tells us that when they formed, there was a lot of groundwater there, because that's the only way that you can actually have these things form. Well, we spent a lot of time after we landed up here in Eagle Crater going from crater to crater. We called it crater hopping because, like I said, this was a flat place, and the only place we could actually see the rocks was exposed in the walls of these impact craters where meteorites had hit in the past. We went to Victoria Crater here, and we spent sort of a second mission, if you will, down here at a very large crater called Endeavour that actually predates the rocks that we landed on. And the goal here was to find out, look, is the stuff in Eagle Crater, is that just sort of a one-off, an anomaly? Or is it part of a very thick sequence of rocks that say that this groundwater and these conditions were around for a really long time? And so we kept looking for bigger craters to see thicker sections of rocks. Now, growing up on Lake Champlain in northern New York, I did a lot of sailing with my dad as a kid. This is waves of sand, not waves of water, but it really sort of reminded me of being a kid and out sailing with my dad. We just had to drive across these endless plains to get to these individual craters to see the rocks that we went there for. So it really was sort of a crater hopping exercise. Now this is Victoria Crater. It's about 700 meters, 750 meters in diameter. It's really deeply eroded. You can sort of see the serrated edge here. And in that red circle right there, that's the Opportunity rover. So this is a little broader view than what we showed for Spirit at home plate, but nonetheless in this high-rise view you can still see the rover. And we actually, after driving along the rim here, went down into the crater and looked at these rocks. What we saw in those rocks painted a picture of, well, maybe Eagle Crater wasn't the conditions that dominated the area that we landed all the time. Really, it turned out mostly to be about wind-swept sand dunes. And if you think about an analogy, you might think about someplace, what they call the Rub al-Khali, or the empty quarter in Saudi Arabia. It's a place where it is very hot and very dry, not hot on Mars, very dry, sand dunes dominate, but every once in a while it rains. And when it rains, the water tends to pool up between the sand dunes and then slowly seep down into the surface. And we saw actual evidence of ripples where water had been flowing through the sand and transporting the sand along. And so the picture that we developed was one that was mostly water in the subsurface, but occasionally at the surface. Habitable, but again, not our Amazon rainforest, certainly not the Yellowstone or Hawaii volcano, something in between, habitable. Water was present here. So after looking at these 3.5 billion year old rocks across the plains, we headed off to Endeavour Crater, and we had our second mission here along the western rim of the crater. And we ended down here most recently at a place called Perseverance Valley. And this is what it looks like. It's a completely different view, at least to me, to you it probably looks about the same, than what we used to see out in the plains. You know why? Because it's not so flat. It's actually got relief. This is the rim of this very large crater that we're driving along. And as we got up to the edge and looked across the crater, the wall or mountain that you see in the distance there is 14 miles away, 15 miles away. It's a long ways away. We started heading down because in orbit, from orbit, what you see here in this sort of patchwork of depressions and small ridges, those ridges are only about this tall. We're looking down. Looked like it could have been an ancient channel. And maybe this was some evidence of direct water flowing on the surface. So we wanted to explore this place called Perseverance Valley. And we were in the process of doing so when the rover mission ended. But these are some of the examples of the last kinds of images that we got. We were starting to look at all these different layers that you can see. Some are brighter, some are redder and more purple. Some are much brighter and they seem to have a very platy appearance. And some of them are sort of very nubbly, almost look like something tossed out of a volcano. And what we started to have pieced together in terms of the origin of Perseverance Valley is one not related to running water, probably. We haven't made a definitive conclusion yet, but more likely is related to an ancient fault that has been exposed to the wind here for literally billions of years, and it's just been wind scoured, and the wind has sort of differentially eroded the soft rocks and the hard rocks to sort of produce this appearance that from orbit looks a little bit like an ancient channel. So Spirit and Opportunity show us that there was water 3.5, 4 billion years ago, but while habitable, wasn't that Amazon rainforest that maybe we were hoping for. Well, let's move on and talk a little bit about Curiosity, because Curiosity wanted to build on those results and start to really poke at that question of habitability. Was there that Amazon rainforest? This is on the floor of Gale crater. It's just a scene that I liked. It kind of reminded me of being out in Monument Valley or someplace in Arizona when there's kind of a dusty atmosphere. And it's something that was able to be imaged by the mast cam on the Curiosity rover. Now this, again, as I said before, is about the size of a Mini Cooper. It's got a mast with instruments that allow us to look around. It's got an arm that's got even more instruments than we had on Spirit and Opportunity, but it's also got this set of instruments on the interior, Chemin as it's called, that blasts rocks with X-rays, and SAM, which heats them up and looks at the temperatures at which certain chemicals are driven off. And I'll just show one example from each of these because they're very diagnostic in terms of what they tell us about the rocks. So where did we go with Curiosity? Well, we didn't go to Gusev crater. We didn't go to Meridiani Planum. We went to an area called Gale crater. Gale crater is about 100 miles across, so it's a big crater. And what's really interesting about it is it's got this giant mountain in the middle. It actually sticks up higher than the rim in some place. And even at this scale, you can start to see that there's layers here, and it looks like there's some channels. And this ellipse that you see is the area that we targeted to land in. What we see from orbit before we landed was that there are clays in these rocks down here. Remember, clays are something that form when the water isn't too acidic, it isn't too, it's Goldilocks. It's just right in terms of when it forms. But as we move up the stack towards younger rocks, we start to see things that do represent more acidic conditions, that represent kind of drying out. Things like what we call gypsum, evaporites as they're called, sulfates as they're called. And then at the top, what we see is something that looks for all the world like a thick sequence of Martian dust. So we go from things that look like they were deposited in nice sort of clement water at the base, to drying out, to dry. And we wanted to go there to sample these rocks to say, what happened on Mars? Why did it go from relatively wet to super dry? And so that's why we targeted this area. Now here's a view from the surface from our mast cam. This is sort of foreshortened, if you will. When you look with a camera sometimes, it's kind of hard to tell how far things are away. But here are some of the units that I'll be referring to. This hematite ridge here, we've also called the Vera Rubin Ridge. It sticks up for some reason. We explored that for almost a year, and while we have some good ideas about how it formed, we're still not absolutely sure. And then right behind it is the clay unit that I mentioned, that we can see from orbit. And then finally, here's that sulfate or gypsum or drying out unit, if you will, above that. And we actually have climbed over the hematite ridge, and we're in the clay unit now, and in the next couple of years we hope to get up into this sulfate. So what have we seen? Well, after we landed, here's the blast marks. This is another one of our high-rise images here. You can actually see the rover tracks here, so it's about the width of a car that you're seeing. We actually headed off in this direction to an area that we called Yellowknife Bay. And the reason for that was, you can see even here the colors of the rocks are different. We thought we saw signatures of clay there from orbit. And so we drove up, we drilled down into the rocks. This is what it looks like on the surface. And we stuck them in our instruments inside the rover. And here's the two slides that I'll show you that relate to that. This is from ChemIn. What are you looking at here? Well, this is from X-rays being sent through the material that we dropped in the instrument. And if you think about like a strainer that has a certain pattern to it, if you hold a flashlight under the strainer, it'll project those things if they're stars on the ceiling, on the walls. But what if they're little slits? Well, then it projects those. And so it turns out that when you zap the minerals with X-rays, because the crystal structure of a certain mineral is always the same, it's like stars or slits. You can look at where the rings are here, how far they are away from the center, their intensity, and say something about what's there. And what's important here is when we look at something that's just like a volcanic rock from Hawaii, there's nothing really down in here. But now, look at all this fuzzy stuff in here. That's clays. So right off the bat with Curiosity, we're starting to see evidence of a lot of clays there. Water in the sort of Clement zone. Here's from our SAM instrument. This is something called a gas chromatograph mass spectrometer. You'll never remember that. What it does is it takes a sample and it heats it up. Okay, and everybody knows water boils at 212 degrees if you're at sea level. If you're in Denver, it's a little lower. Different kinds of things have different melting temperatures. Or they have different temperatures at which they will release the water that they're holding on to, because some have tighter bonds and some have less tight bonds. And so when you heat things up, the temperature at which water comes off, in this case quite high, tells you something about where that water was occurring in the sample. And it turns out for this, it's occurring in clays, and it tells us it's a particular kind of clay. Smectite in this case, you don't have to worry about that either. It's just that now we've got two lines of evidence that from the first rocks that we drilled into, clays, they're there. There was water there. It was the right kind of water in terms of being clement for life. Habitable. Well, since then, that was Yellowknife Bay over here. We've driven all the way down here. Remember that view I showed you with the hematite ridge and the other things in the distance? Well, we've actually crossed that ridge now, and we're into that clay unit. We've gone, I think, on order of 20-some kilometers at this point. And you can see our traverse and all the names for the rocks that we've gone by on the way. And I'll zoom in right in here because this is where we are today. We're right up in here on the backside of this ridge on this clay unit. And I was on shift on Monday and Tuesday of this week, being the long-term planner, keeping our eye on the prize while all the shiny rocks that people wanted to drive up to, and trying to understand why this clay unit's there and how it formed. Well, here's a clue. These rocks are actually before we got to the clay unit, and what's interesting about them is you can kind of see them edge on, but they're not flat, they're tilted a little bit. They're tilted kind of downhill and to the left. Uphill, the wall of the crater is to the right. And then when we drove a little further out into the crater, we started to see this stuff. Completely flat-lying rocks, spaced like millimeters. You know, really finely grained sediment clays that are deposited like this. And so the conclusion here is that when you add the chemistry together with the morphology, how the rocks appear, this is evidence that there was a lake in Gale crater, in this case about 3.2 to 3.5 billion years ago. Really pretty old, maybe about the same age as Meridiani Planum and the blueberries at Opportunity saw, but we've seen over 900 feet of this stuff now. So think about how long it takes for 900 feet of clay to be deposited in little layers like this. Can't do it in a year, probably can't do it in 100 years or 1,000 years. It's more like tens of thousands or hundreds of thousands or millions of years. So there was a lake, a big lake, in the floor of this crater. Those tilted rocks that we saw on the last slide, that's from the delta that was draining from the wall of the crater and washing the sediment out into the lake. We're talking about something here that was around for a long time. And what's interesting about the lake is you can't isolate it. It's not like there was a dome over the top of the crater. If the conditions were on Mars were such that a lake could be here, then the conditions were such on Mars that there were lakes elsewhere. So now, we're not quite to the rainforest yet, but we're headed in that direction. Now, we do see lots of things that are non-lake-like. This is a modern sand dune, and I put it in here because I think it's a really cool image. This is a Namib sand dune that we drove up to and sampled. And it turned out while we were here, there was actually a lot of sand blowing off the top of this. So we actually got to see an active sand dune on Mars. Here's the Vera Rubin Ridge, this hematite ridge that I showed you in that first slide when I started talking about Curiosity. You can see part of the rover here. This was actually taken by our MOLLE instrument, which is a hand lens, and it's looking along the ridge. You can see it actually sticks up. There is hematite in this rock, and apparently it makes it more resistant to erosion. We're not quite sure how it got there, but in a manner similar to what we saw in Meridiani Planum, it probably was after the lake was here and groundwater was flowing up and depositing hematite that made this harder. We drop down off the other side of this. We see the clay unit. This is where we are now. You are here. That's where we are today. The hematite ridge is here. So we drove up over the top of this and down. And you can see the character of the rocks, the character of the surface changes dramatically from what we've seen on the other side of the ridge. We just sunk in our first hole. You'll see this was done over last weekend. This just came out as a press release today. You can see the pre-drill, the shininess there is where we actually tried to polish the rock to get a clean surface to do some chemical analysis. And what's interesting about this is you can see that when we drilled and tried to retract the drill, it actually broke the rock and pulled it up a little bit. Now, very preliminary results, but hey folks, we're seeing more clay. You're probably getting really bored of me talking about clay. But if you're interested in habitability, if you're interested in the possibility of life, water, clay, wow, now we're talking, at least to me, as a geologist, because I'm not a plant guy, but this is sort of the geologist equivalent of the Amazon rainforest. So what awaits us here? Well, we're down in, this was the ridge that we went across, our clay units here. We're actually right about over here where my pointer is. And we're going to head up onto this surface that we've named the green hue pediment and up into those sulfates that you see that are sort of black and brown and white over here. And see what happens. When do the clays go away? Why did it get dry? What are the chemical signatures that tell us what happened to Mars 3 billion years ago or so that led to a planet now that's so cold and dry? Now, just as a sort of sidebar, because it's recently happened, the InSight lander set down on the surface of Mars just after Thanksgiving last year. And its goal isn't really the same as the rovers that I've been talking about, but it's very important because what it's doing is it's sort of taking the heartbeat, if you will, of the planet. It's trying to find out how much activity, geologic activity, is going on in Mars today. How much heat is still in the planet? Does it have a liquid core? And so we've put out these instruments, the seismometer and a core, a heat probe that goes down through, and we're trying to sense that information. It's a mission that's going to go on for about a Mars year. It's just begun. We're going to stay tuned for the results that come out of this, but it's kind of interesting that you can actually look down on this lander. This is another high-rise image, and you can actually see in the box over here, if you look closely, this is a sequence of 2 images. You can actually see the difference between when the seismometer was put on the surface and before it was on the surface. This is the view from InSight. Looks quite a lot different than what we saw in Gale, Opportunity, and Meridiani, and Spirit, and Gusev. Looks a lot like the Viking landers. We actually intentionally picked an area here that was quite flat, where we thought there weren't very many rocks, where we could get these probes down into the subsurface. So this is another piece of that puzzle, because it tells us something about how geologically active Mars is today. And from that, we can kind of back up to that 3 billion years that I was talking about before, when things apparently changed in the past. Okay, what's next? Well, the Mars 2020 rover, guess when that's going to launch? It would be Mars 2020. It's got a whole set of instruments. They're different than what we have on Curiosity. This is geared to actually take some cores and leave them behind. It's sort of the first step in sample return. It'll cache samples that a future mission can go and pick up and return to Earth. And its job is to build on the results of those previous rovers and say something about this life question directly. Okay, now we know there was water. We know that it was habitable. But was there life? And the instruments that we see here are geared towards answering that question, really kind of poking at the details of the rock to see if we see the chemical signatures or the physical signatures in the form of fossils, perhaps, that tell us something about the past occurrence of life. Where do you go to do that? Where do you pick a landing site to do that? I mean, here's a map of Mars. I'll explain it here. What you see in white is where we can't go with this lander. Too high latitude, harder to get to and too cold for part of the year. So can't go there. Everything in black is also too high. Can't go there. You don't have enough atmosphere to be able to slow down before you do the bug on the windshield thing. So you got to land lower than that. So you start to get into these areas where you see the colors here, where you can actually land. Every red dot that you see, every yellow dot that you see, and the few green dots that you see were candidate landing sites for that 2020 rover. Somebody in the science community said, you should go there. And we had a series of 4 landing site workshops where somewhere on order of 150 to 200 people come, and they get up and they say, you should go here, and everybody says, why? And we discuss it. And it turns out from the first 1 or 2 landing site workshops, we really couldn't vote anybody off the island because we didn't have enough information. So what those first landing site workshops were, do you meet the basic requirements in terms of being low enough, being at a low enough latitude, et cetera, but let's go get more data. And by the time we dug into the 3rd workshop and eventually the 4th workshop, then we start talking about religion. Because what happens is certain people think that a certain type of landing site is the best place to go. And other people think another type is the best place to go. Now with Spirit and Opportunity, you remember I described we went to an ancient lake bed, and we went to one where there was hematite. You had 2 rovers. You could go to one of each. There's only one of these guys. And so you can bet that those discussions really became, heated isn't the right word, but let's just say that we plowed the same ground several times in terms of coming back to a conclusion. And we really started to zero in on a couple of places. Right up in here, Jezero and Northeast Syrtis, and another one down here, Columbia Hills. Why did we want to go there? Well, let me explain this slide. What you're seeing on the left is actually sort of a map of the landscape. It's showing the elevation of the surface with blue being and purple being low and yellows and reds being high. And for example, here in Jezero, you can see a crater that's on order of about 85 miles across. Here you see in Northeast Syrtis, it's sort of a jumbled terrain with no specific craters. And then here, Columbia Hills, that's actually Gusev crater. We've been there with Spirit. These are our 3 final sites. And these are our 3 religions. One up here, water lane deposits. One in the middle, that chemical signature, much like hematite. And down here, remember the silica that we saw with Spirit and Gusev crater? Remember those little nodular things that I showed? Well, it turns out that there's a really wonderful analog for those things in hot springs, or springs, down in South America. And where you find them in South America, they're associated with biological activity. Now, what we don't know is, do they only form in association with biological activity? But that's certainly an intriguing possibility. So here's our 3 sites. Here's sort of a broader view of the landscape. I showed you this one before. It's where our wheel dragged things up in Gusev crater. This is just these different kinds of minerals kind of splayed out all over the place. The idea in this middle one is groundwater altered the rocks, and then erosion exposed those for us to look at. And then up here in Jezero crater, we're going to go look at a delta. And here's some of the details that we see here. Well, at the 4th workshop, after a lot of discussion, remember I said we plowed that ground a few times and a few times again, we ended up settling on Jezero crater. And the reason why, you can actually see there's a channel that flows in right here, and then at the same elevation, there's a channel that flows out. And what that does is it tells you that there was a lake in here up to that level. And if you look right over here, that red box is what's blown up down here, and it's one of those first slides that I showed. This is an orbital view of a river delta formed when a river drained into Jezero crater, and the colors that you see on here, this is sort of the ancient sort of channels splaying, think the Mississippi River Delta. Geologists call them bird's foot deltas. The minerals vary with color here. and the greens and the oranges are clays. And so the decision was made by the associate administrator at NASA after all these conversations, after all these discussions from our 30 some odd that we started with, that 2020 will land and explore this deltaic deposit that formed, again, 3.5 billion years ago in Jezero crater. So I think, is that my last slide? I think it is. With that, I will stop and see if folks have any questions. It didn't play, but that's all right.
Raise your hands if you have a question. I'll come by with your microphone. And for our worldwide live stream viewers, if you could type in your question, we will try to get to those as well. So,
let me see if I
Jackie,
can.
I'll start with you.
In watching your slides, are you aware that there's a crater about 80 miles from here? It's called the Roblo Osceola crater in Missouri.
Yep.
And there's round rocks all over there. There are accretion rocks.
So there's not a lot, but there's a number of craters all over North America and the world. They tend to be quite eroded. I live near Washington. There's a big one buried in the rocks in Chesapeake Bay. I did part of my dissertation out at Meteor Crater in Arizona. A lot of those rocks have been, in their erosional process, have been subjected to a lot of water, and so you get concretions and other things forming there. So they're analogous, but they're not direct analogs. But yes, I'm aware of the one that's nearby.
Well, if you want one, I got about 20 out in my yard.
Do you? I'd say send it to me, but the postage might be pretty expensive. But I probably will take you up on that. I'd love one.
Dr. Grant, the video's playing. That's on Mars,
Oh, is it
right?
playing now? Okay. It's playing really fast, though, isn't it? So this is a panorama that was taken by the Curiosity rover when we were up on the Vera Rubin Ridge, and it's just sort of panning around. It gives you a sense of the scale. This gives you a sense of our traverse since we landed. So it was just there to have you stare at something besides me while people were asking questions.
All right, we have a question over here on your left. Coming to you, sir. Just hold it close to your mouth.
Hi, I'm hoping this is not like completely out of your wheelhouse, but I'm kind of curious with planning for the 2020 rover and whatever missions are going to come after that. What are the prospects for using things like artificial intelligence and machine learning and things like that for helping with future Mars exploration?
That's out of my wheelhouse, but as you can tell, I like to talk. No, so one of the things that's interesting is that the technology that you're using in these spacecraft really has to be sort of tried and true. That's not to say that advances are not incorporated. You know, my phone in my pocket in many ways does have a lot more computing power than anything on board the Spirit and Opportunity rover. I mean, that's just a fact. So I think it's going to be very important. But on the next mission on 2020, no, that design is really locked in. With sample return, which is going to follow hopefully within 10 years, you know, who knows? It's going to be a more simple mission in the sense that its job will be to largely go and get the samples that Curiosity has placed for it, has cached for it to pick up. If that happens in the next few years, then probably not a whole lot. But at some point, clearly that kind of technology is going to be enabling. How it's going to get worked in, when it's going to get worked in, I don't know.
Dr. Grant, we'll stay on your right here, about midway back in the room.
Yes, you talked a lot about clay, and you sort of used it generically. What kind of clay are we talking about? Kaolinite, bentonite? I mean,
mostly things like kaolinites, aluminum, and sometimes iron-rich clays.
Yeah, well, you mentioned hematite.
Yeah.
Isn't that iron?
No, hematite's not a clay. Hematite
No,
is
it's not a clay.
an iron oxide.
It's an iron oxide.
But the different clays that form, they tend to occur in layers. So there was a candidate landing site, not only for Curiosity, but also for 2020, in an area called Marth Vallis. And one of the things that was very intriguing about that was there were aluminum clays overlain by iron-rich clays. And the thought there was that maybe you were looking at an ancient weathering horizon. If you've ever been down in the southeastern United States, you know, they have these orange soils. And a lot of stuff's been leached out of those down into the subsurface, and you get these chemical zonations. While that's intriguing, and it certainly says a lot about the role of water, if that interpretation's right, soils tend not to preserve a lot of biological material other than in the uppermost portion, which has been lost here. So one of the reasons why that place didn't get picked is why I just described, but you do see these sort of stratigraphies or layers of the clays in some places. In other places, they're scattered around.
So there's a lot of silica, which is the most common element we have.
No, it's
here
not
on
a
Earth.
lot. We see it in some places. So there's a lot of it along the edge of this small volcanic edifice in Gusev crater, but we don't see it in a great abundance in very many places on Mars. It tends to be pretty rare. And that's actually telling you something, I think, as you were leading up to. On the Earth, at the surface, silica is very common. And it's because of volcanic reprocessing. When our planet, you know, the heavy stuff went to the middle, the iron nickel core, the lighter stuff, you know, the soup skin on the outside, that's the stuff that we're walking around on. And then it's been reprocessed through plate tectonics. You tend to get minerals that are more and more stable at lower and lower temperatures. You don't see that on Mars. It tells you, not only from the landforms, but there hasn't been this long-term sort of reprocessing of the material on the surface to get to those kinds of minerals. It's sort of more basaltic like Hawaii. Yep.
John, we have a question way in the back of the room here by a young man.
Hi. I've enjoyed the discussion so far, and my other question I was saying, so there's like NASA's like scheme by like the 2030s and 2040s and whatnot to return humans, or not to return humans, but to place humans. What is it that Curiosity and say the Mars 2020 rover, they have all this equipment on board. What are they not able to achieve that, say, a human mission would be able to?
Yeah, so that's a really good question. 15 years is how long the Opportunity mission lasted, plus or minus. Okay, it went a little over 40 kilometers. What's that, about 30 miles, 25 miles, something like that. 2/3 of 40. Makes my head hurt. Okay, I don't run marathons, but I could walk 25, 30 miles in a couple of days. And if I took my time and picked up the interesting rocks, I could probably do it in a week or two. And if I really took my time and thought, well, that one I should have stopped and gone back, and I went back and forth, okay, maybe a month or two. So the ability to sort of have this rapid feedback and analysis and move around with your brain there instead of waiting for a downlink and then sequencing something and uplinking it allows you to do things, I think, in a much more, well, faster, but also in some ways more comprehensive. Because the term that we used when we were on the rover was you never know when it's going to die. So do we go back to a rock that we thought was interesting, or do we keep going? But if you're there and you're going to be there for a while, well, you can do both. So I think there's a lot of flexibility that humans offer in terms of their ability to do the science there, that robotic missions, as stunning and as spectacularly successful as they have been, hey, let's face it, humans can't go to Mars now. So all we have are these robotic resources, and they're doing a great job.
Well, let's stay in the back of the room here for the next question.
I think he's coming.
Thank you. First, I want to thank you for getting up there and sharing a little bit of what you know. I'm wondering, what is the protocol when you guys make a discovery? For example, if you do discover evidence of ancient life, how does that get delivered to the public? And what do you think would happen culturally?
Well, we would go back to the warehouse where all this stuff is staged. To me, the whole thing, so I'm a geologist, I am not a biologist. I get this stuff by osmosis. And I'm fascinated by the possibility that, I think I said this earlier, holy crap, there was a lake in this crater. Maybe I didn't use those words. To me, I mean, I told you I grew up in this big Lake Champlain in New York State. I mean, that's habitable. And that for me was that was a moment where I was like, maybe there was life on Mars. And I've always wondered, what are the odds that humans, that the Earth as sort of a abode of life is unique in the universe? And, you've heard the billions of billions, and you've seen all the news recently about planets from the Kepler mission, for example, that may be in this habitable zone. Heck, it might have been the planet right next door to us that had life. To me, that's really sort of fundamental about our place in the universe. So to me, I'd be excited as heck. I don't know how it would be presented to the public. We haven't had to yet. But stay tuned, because while we certainly have no evidence of life on Mars, it's not like we found this harsh, completely inhospitable place. This is worth continuing to look for, at least as far as I'm concerned.
Dr. Grant, we have a question up front here from a future scientist.
How fast do the rovers move?
Really not very fast. They go, so Spirit and Opportunity go 6 feet in a minute, 2 meters a minute. So let's see, that's 1, 2. That's a minute. Remember what I was talking before, it went 25 or 30 miles in 15 years now. We didn't use it the whole time, and we stopped in places for a while, but it doesn't go that fast. A lot of questions that I get are, I didn't talk about this a lot because it was mentioned in the bio early on, but on Spirit and Opportunity, I did something called a SOG chair, S-O-W-G. You don't care about that. But what it meant was every day when a group of scientists got together, they would all say, I want to go to that rock, I want to go to that rock, I want to do this, I don't want to go to any of them, I want to keep going. Okay, it sounds like maybe your dinner table when somebody says, what do you want for dessert? So my job was to sort of herd the cats and come up with a conclusion that said, well, we have this much time and we have this much energy, and our goals of this mission are A, B, and C, so we're going to do this. And that's what I would do on a daily basis. And I forgot where I was going with that, but it had something to do with your question.
How fast did the rover?
Speed. People say, what's it like to drive the rover? Because people say, well, you got to decide what you were going to, thank you for that, Eric. People would say, what's it like? Is there a joystick or something? And the answer is no. The way we do this is we would look at where the rover was today and we'd say, boy, that fountain looks really cool. Let's go there tomorrow. And we would send the commands up to the rover to drive this way and then drive around you guys and go to that fountain. So it was a very slow process. I finally answered your question. You'll never ask another one, will you? You can.
Do you have another question?
I'm sorry.
There was another hand up front
I
here.
think up here in the front row.
Yes, sir. Yes, ma'am. Let me.
It was referring to the person that asked the previous question in regard of, instead of just sending computer to Mars, what about sending humans? So I was thinking, okay, if you had the InSight mission that took 6 months to get to Mars, so if you send humans, so how long do you think? So I mean, because we're talking about it's a very long journey compared to just going to the moon.
Yeah, I mean, it's days.
So
it's
that's
days. To the
why
moon, it's days
I
to the
was-
moon. Days to the moon. It's months to Mars.
So when you talk about 6 months in Earth
It's really far.
time, how long is that? I mean, they left in June, they arrived in November. So it's a 6 month what it took
Actually,
to the
May to November,
May
yeah.
to November. So I was
It's a long.
wondering.
It's 110 million miles.
Exactly.
Where is she?
That's what
There
I-
she is. She landed that sucker.
That's why I was wondering, like,
Sorry.
I don't think we're so far away from even reaching to a level of sending human.
Well,
I just
so-
wonder.
Right. So if somebody said tomorrow, you will launch humans to Mars, the answer is we can't.
Yeah, of course.
Okay, but if we start, but we have all these things, they call them, you're going to love this, they're called critical knowledge gaps, okay? And there's even others, there's the unknown unknowns, okay? There's known unknowns and unknown unknowns. So you can start working on those things, okay? Okay, if we don't start tomorrow, then tomorrow when they ask that question, the answer will still be, we can't. But if tomorrow we start answering the questions, we're going to get to a point where a year, 5 years from now, 2024, we're going to say, we can. So until you start that process and really become wed to it in the sense that, by God, we're going to do this thing. We can't change our mind every 2 or 4 years. Maybe we'll get there.
All right, we have a question about midway back in the room. Due to the time, let's do 2 more questions. We got one here. I know there's a gentleman in the back that has had his hand up for a little while, so we'll start here.
Yeah, so if indeed there was water on Mars, I'm just curious what the leading theories are as to why it's dry now.
Okay, so we know we've lost, there's another mission that's very exciting. No, it's a very exciting mission. It's called Maven, but I'm not involved in it, so I didn't talk about it. No, that's not true at all. I actually don't know much about it. But what I do know about it is that one of its goals was to look at the ratio of different kinds of materials in the atmosphere to say, well, if this one's a little heavier than that one, then over time, if you see concentrations of the heavy one, then you must have lost a lot of the light ones. And you can do that sort of thing to get a sense of how much water has been lost. And it turns out it's quite a lot. You see different estimates of if you made a layer around it like frosting around the whole planet that was just water, it's, tens of feet or something like that. And then if you look at lakes and streams and things like that we think we see, well, then maybe it was hundreds of meters or hundreds of feet. And then there's some people who think that at one time there was an ocean that covered part of the northern hemisphere of Mars. And then maybe it was, hundreds of meters to maybe 900, 1,000 feet. So there's a lot of uncertainty in terms of how much water was there. We know it was more than there is now. We know some has been lost to space. We suspect the rest of it is still there, it's just gone underground. Because what's happened on the Earth with plate tectonics is you recycle this stuff. And on Mars, once that engine shuts down, or at least becomes very slow, you stop getting that material back out to the surface. So that's probably where most of it is in the subsurface.
All right, Dr. Grant, back here towards the back of the room.
In your, excuse me, in your talk, you've dated most of these geological features 3-4 billion years ago.
Yeah.
Okay,
Kind of flip, huh?
How did you choose those dates?
Yeah, it's a really good question, and I like it when somebody asks me that because it's complicated, and I like to talk. So, so there's 2 ways. So, the main way that we do it is using the number of impact craters that we see on the surface. Now, we had a comment here before about a crater that's here in Kansas. On the Earth, relative to the rate at which meteorites and asteroids hit the surface of the planet, other processes, running water, the wind, plate tectonics, volcanism, operate at a much higher speed. So there's very few craters that we see. But on Mars, which geologically has slowed down, there's a lot of time for those craters to accumulate. And we know from the moon, for example, when we go to the lunar mare, where we landed with the Apollo missions, and we could count all the craters and bring back the rocks and then do radioisotope dating, we could tie those chemical data to the number of craters and get some sense of what we call the flux, the rate at which these craters form over time. Now, it turns out that craters that are big are formed by bigger asteroids, and they're a lot less common than little ones, because if you take a brick and hit it with a sledgehammer, you get a few big chunks and a lot of little ones. So you look at the size of the craters and how many there are, and you say something about how old it is. For Mars, there's more assumptions, because we're closer to the asteroid belt, we don't have a lot of radioisotope dating, and so on old surfaces, I think the estimate is, yeah, when you use the craters to get an age, it's probably good to within a few hundreds of millions of years. But by the time you get to something that's younger, where there's not many craters, sometimes it's a factor of 2, which makes a huge difference. Is it 1 billion year old or 2 billion years old? So with the Curiosity mission, with that SAM instrument, we were actually able to do potassium-argon dating, something we do on the Earth with rocks. And we were actually able to get an age that was quite close to what was estimated using the crater densities. Now, we're not there yet, But when I say 3 billion years or 3.5 billion years, and you come back and say, well, I think it's 4. Yeah, you might be right. But it's really old. It's really old. It's not like, you know, you look at the Earth, and most of the rocks that we see here are in the last 500 million years or 1 billion years. So there's a window here back in time on Mars. You can argue whether it's 3.5 or 4. It's really old.
All right, thank you, Dr. Grant, for a wonderful talk.
Thank you.
And thank you for attending tonight's program. Please visit lindahall.org and sign up for future events, and I hope to see you back here soon. Thank you and good night.